Okay, if everyone is ready to begin, we'll start with Gergely Bérczi's second talk on non-reductive moment maps and cohomology of quotients.
All right. So thanks very much. And in this second talk, I will focus on explaining what I promised. This is what we call the blow-up procedure for in the non-reductive picture. So is it true? And then I just put this. Is it? Can you hear me? Okay, is this better? Okay, so in this second talk, I will talk about focus mainly on how to. So first, in the first half, I will explain how to extend this GIT blow-up procedure, which is known for reductive groups, how to handle the situation where we have strictly semi-stable points in the space. And then I will talk about cohomology of non-reductive quotients and how can we describe these quotients using an extension of moment maps for non-reductive groups. So that's the plan for today. And let's see how far I can get. So I start with a small and quick reminder. So we have, this was the setup yesterday. So we have a irreducible U hat variety. So a variety acted on by a graded C-star extension of a unipotent group. That's what I call U hat. Or more generally, for any graded linear algebraic group. Grading means that we have at least a C-star inside the reductive part of the group, which has positive weights on the lineage of the unipotent radical. So it's a technical but mild condition for the group, but it helps us to control the orbit space. And this was the setup which I will use today. So Z-min, I use this notation, Z-min for the minimal weight space in X for the C-star action. And X-min is this open Bialiska-Biola stratum. So the attractor of the, the set of points which are attracted to Z-min under the C-star action. So, and so the theorem I just repeated here. So if we have the so-called semi-stability equals stability condition, so the stabilizers, the U stabilizers in Z-min are all trivial, and we have a well-adapted linearization which can always achieve. So we shift the linearization by a central character to achieve this. Then what we can prove is that what I call the enveloping quotient is a projective variety, and therefore the invariant ring is finitely generated. So this enveloping quotient is Proj of the invariants. And moreover, in this case, the stable locus for the U hat action is the same as the semi-stable locus, which means that this action on this set is, the quotient is a geometric quotient on this set. So it's really just have a very simple description. You take this Bialiska-Biola stratum and take away the U-sweep of Z-min. And it's really has the same, this Hilbert-Mumford picture. So the point is semi-stable if and only if C-star semi-stable for any U shift. So that's the picture. And so the question is, the next question is what to do.
I'm not totally sure if you said what well-adapted means yesterday.
Sorry again?
Well adapted. I'm not convinced.
Yeah, I explained it yesterday. Well-adapted linearization means that we have the C-star action, and we shift this linearization by a central C-star. By a character, which such that the origin sits just above the minimal weight. So that's what I explained yesterday. It's a technical condition which we use in order, for instance, here to describe. So in this case, this means that what is the stable locus for the C star action? So what is this set here? Because the weight is really just above the minimal weight, we want that minimal weight coordinate to be non-zero, and at least one other coordinate is non-zero. So, so the stable locus is really just this x min minus z min for the C star action. And for the U hat action, we just have to take the U sweep of z min, and that's what we take away from that. Yeah. So, so the question is, what happens if we have this situation, which happens in most applications? So if you're not, unless you are super lucky, then we have strictly semi-stable locus in our moduli picture, GIT problem. So if in this case we have, you know, the quotient parameterized is closed orbit. So if you take a polystable point, so the orbit is closed, then what can see is that the stabilizer of that point is reductive. That's a very important, crucial fact. And so it means that the maximum dimensional stabilizer for points in the semi-stable locus is reductive. So we take this, I noted by XSSD, is the set of points in the semi-stable locus where the stabilizer has dimension d. And we take d max, that's going to be my notation today, also in the non-reductive setup. So d max we always stand for the maximal dimensional, it's maximal dimension among the stabilizers. So those. So in the reductive case, if you blow up the semi-stable locus along this maximal locus, sort of where the stabilizer is maximal, then what we can see is that after the blow up, Dmax will strictly decrease. So in other words, Dmax is a ranking, it's a Lyapunov, it's a ranking function for this blow up procedure. So it guarantees finite termination if you repeat. So yeah. So in the non-reductive case, the picture is less clear. So we have obvious and straightforward candidates for blow-up centers, but it turns out they don't work out as well as in the reductive case. So let's see the picture. So in this case, we have this is this projection map which we use all the time. So we have this is the contraction map or the Bialy-Skibirula map. So from the Bialy-Skibirula stratum to Z min, which sends a point to its limit under the C star action. Then again, I just follow and adapt the same notation here. So Z min D will be denoted some stratum in Z min. This is a set of points where the U stabilizer has dimension D. And the same for X min. And so it's a general fact that the stabilizer of the limit point is never smaller than the stabilizer of a point. So, and that means that if you take the U sweep if you take the Dmax, so the maximal part, that's kind of the smaller stratum in this stratification for based on the size of the stabilizer. You take the U sweep of this smaller stratum that's contained in X min Dmax, and that's contained in the pre-image of Z min Dmax. So we can see here at least two obvious candidates for the blow up. So what is important is that UZ min Dmax, that's what I want to say here, is equal to U hat Z min Dmax because its points in Z min are C star stabilized. So, and that's a closed subscheme of X min. So in principle, we can use this as a center, right? And that's actually we will do. So we have two candidates for the blow-up center, which is just with U times Z min Dmax and X min Dmax, right? These are not the same. One contains the other, so this one is usually smaller than the other one. So the question is, what happens if you start blowing up at this locus? And for if you have in a more general setup where we have a bigger reductive group, reductive part of the group, then obviously you have more choices, more candidates for this blow up, natural candidates. So now I just show you, maybe I show you only the second example. Yes. So I have an example of I have two examples here, very simple examples, where we show that this x min dmax and u times z min dmax is not enough. So this is a small example for x min dmax. So the group is just this Popov-Pomeranian type group, so it's C plus 2. So it's a two-dimensional additive group. And you can check that if you take this, so that's this 3x3 matrix group acts on the left on 3x n matrices, which are denoted by the rows R1, R2, R3. And the point is that we can pick here a grading one parameter subgroup. It just means that the weights along the diagonal are strictly decreasing. And it turns out that in this case, the Z min is the projectivized last. So matrices with 0 first and second row. And since the action is really adding the second row and the third row to the first row, this is just the action here. U2 times the second row and U3 times this last row we add to the first row, you immediately see that there is a locus where the stabilizer has dimension 1, where the second two rows are collinear or linearly dependent. It turns out if you now blow up along this x min dmax, this is x min 1, so this is the locus where this is just this locus where the rank of R to R3 is 1 and R1 is arbitrary. If you blow up along that, then it remains. So we get the same dmax. So we still have non-trivial stabilizers. But I would like to focus on this other example a little bit more because this is less trivial, and this is what we'll actually use later. So, and it's kind of silly, but it took us some time to come up with this counterexample because it's not easy to find. So in most examples which you write down, you have this center as a blow-up works. So this means that the dimension the Dmax will decrease by strictly decrease after doing this first blow-up, but it turns out that it's not the case in general. So I would say we found this example like let's say almost accidentally and after like years. So so it's a very simple example in the end. So we take this 4x4 matrix group in GL4, and it's a U hat. So it's just a C star extension of a unipotent group. You see that we have TT11s on the diagonal. So, and this is a Popov-Pomeranian type group. So generalized, so it's a regular subgroup of GL4 with parameters in SV. Sorry, this is actually not, it's a generalized Popov-Pomeranian. So we have two parameters which are the same. So this V and V at these positions are the same, and S is a different parameter. But it turns out this is a group. And it acts again as a left action on projectivized 4x n matrices. So the action is kind of clear, like geometrically, just, we can describe the necessary subset. So the Z min is going to be the subset where the first two rows are 0. And inside that, there is a Z min Dmax, where Dmax is 1. So there are points in Z min where the stabilizer has dimension 1. So there's a non-trivial stabilizer, U stabilizer, and that's this stratum, this smaller stratum, is the set where the first three rows are 0. Yeah, you can see that if you take this set, so the first three are 0, then this S parameter can be anything. So this means that this Dmax is 1, and the stabilizer of such a point is the subgroup where V equals 0 and T equals 1. So that's the stabilizer here. This is what I denoted here by U prime, by the way. It's just the same as U prime. So now we blow up at the U sweep of what is U sweep of Z min D max. So Z min D max is this very simple set where the first three rows are 0. If you take the U sweep, it's just where R1 and R3 is 0 and the rank of R1 R4 is 1. So then take a point, we can take one point over the, so if you take the blow up at that and we take a point over Z, we can take a point this Z in the center. That certainly sits in Z min U times Z min D max. And if you take this point over that in the normal direction, so if you take this parameter here, which sets in the same position as this one, and one can check that the stabilizer of this point is representing this point in the blow-up is the same U prime, so it's the same group as this one here. And the reason is simply because what you can see is that if this holds, so if R2, R3 is 0, then that somehow the action along the normal directions is trivial. So that's a very simple example that shows you that this doesn't work. Like at least it's not as, not immediately. So you have to do something. And then I took as a, so there is a kind of after. It's in the end of the day, the kind of the algorithm which I show you is pretty simple. It somehow took us a while to find this, but we managed to finish this last year with Francis. So what we found is an iterated blow-up procedure where we always blow up along this locus, which I'll show you, but it's not enough to blow up once. And the lexicography pair, so you have to not just record the D max, but we also have to record the dimension of this subvariety, the dimension of U times Z min D max. And it's going to be, it's not a ranking function, but it's a delayed function for the non-reductive GIT blowups with delay free. So, and hence the blowing up procedure terminus. So I've explained what this means, but in a second. So it means that, so if you blow up first along this locus, U times Z min D max, and we blow up iteratively, and so we see what happens. So if after each blow up, we check whether D max really decreases or not. If it remains the same like in the previous example, so if it doesn't change, then after at most 3 iterations, so it might happen for three iterations after each other, but after at most 3 of them, we have the dimension of U times Z min D max will increase, strictly increase. Which means that we are, applying this, using this procedure, we get to terminal states, which can be this one, 2 different types of terminal states. The first type is when you have a codimension, where the codimension of U times Z min D max is less than or equal to 1, so we can't even start, so we can't go on with blowing up. That means that if this is 1, it automatically implies that Z min D max is Z min. And in fact, in this case, if the codimension is 1 and we have a homogeneous Z min with respect to the stabilizers, then the quotient can be identified simply with Z min. In the second case where D max is 0, this is what we want to achieve. This means that the stability equals semi-stability, because this means that all stabilizers are trivial in Z min. So that's kind of the picture for unipotent, for graded groups. And that's the general procedure which works. And I'm pretty sure there should be a stacky interpretation of this, which I'm really looking forward. So yeah. Well, that's yeah x min or yeah. Yes, the same So once I blow up, I take the semi-stable locus again, and I do the same. So I take okay. So there is a So there is a So was the linearization above. So we twist a little bit with the exception divisor, and then we pick. I mean we keep the same grading one parameter subgroup along the process. What do you mean? No, I mean. Yeah. The same semester. So we use this. So when we do the blow up, you get another. There's a U hat action on that, and then we just use the same. You take x min hat minus u times z min hat. There. That's the semi-stable locus. So what I mean, so we don't have to take, you don't have to, sorry. So if you do this, you don't have to take semi-stable locus right up there, because I'm just talking about Z min. And if you take the blow up, then you can take the corresponding Z min there, and you can determine the stabilizers. You don't have to worry about semi-stability there yet, right? Sorry, because I'm just taking the new Z min, and I'm taking the new Z min there. And yeah. So exactly. So we don't have to worry about even the linearization, because in that sense, Z-min is determined by the grading one parameter subgroup, and the stabilizers are also determined by them. So
Question. So I just wanted to understand better, what is the problem one is trying to solve by this? I mean, you're describing a procedure of iterated blow up, and I understand that at the end you end up with semi-stability and stability coincide. But is there, is there some universal property? Is there some way to formulate what the end result is supposed to achieve in terms of the original group action on a variety?
Yeah, so in that sense, if you, I mean, there's no modular interpretation of the new stable points, if that's the question, unfortunately. Yeah. No modular interpretation. General. Yeah.
But it's not clear. I mean, it's a procedure. It doesn't tell you what the, interpretation of the end object in terms of the original problem is.
So
and there may exist many procedures to get rid of,
Yeah, there's if I don't think that applies here, but actually we get rid of even the finite stabilizers here, right? So in the end of the day, we have, so in the end of this procedure, we have really trivial stabilizers. Yeah, exactly. So yeah. But there's no modular interpretation, automatic modular. So if for a concrete problem, we can't describe those as some sort of object. Okay. So and so the next in the second half of my talk, I talk about moment maps and how to describe this GIT quotient, non-reductive GIT quotients, as a symplectic reduction. So it's kind of generalizing the reductive picture described by Francis's thesis. And so for this, we kind of introduce moment maps, which for the non-reductive group actions. So I will start with reviewing the situation in the reductive case, and then explain the corresponding picture for the non-reductive action. So let's start with the symplectic manifold and the compact Lie group which acts on X. So this is a little bit meant to be also for students. So it's a very mild introduction. So for a symplectic manifold with a compact group action, a moment map is defined as a map from X to the dual of the Lie algebra of the group, such that it's satisfied this preserved equation. So the contraction along the infinitesimal action of a Lie algebra element is the same as d of the pairing of nu at A. So this is the natural pairing between the dual of the Lie algebra and the Lie algebra, and this is the infinitesimal action. So if we start with the complex projective varieties, so X sitting in Pn, and it acted on by GLN, a complex reductive group, which is a complexification of its maximal compact K. That it means that we have a representation of this G in GLN plus 1, such that the maximal compact subgroup of G sits in the unitary subgroup. And so we have a natural choice for the Fubini study Taylor form, and then the action is a Hamiltonian with this moment map. So we have a very precise and concrete description of the moment map in this case. So whenever you have a Lie algebra element, then we can take that corresponding component of the moment map. So it's really a map from X to R, which is just we take projection of the moment map on this in this direction. And if X is a scalar, then actually we this equation holds. So the gradient of this function, this component, is given by I times the infinitesimal action on the variety. So this is kind of the things which we use in studying the geometry of the moment map. So what is the reductive symplectic reduction picture? So if G is a complexification of K, then and acting on this projective variety X, then the semi-stable locus can be identified, is equal actually, those points on the level set so it's going to be those points on the level set of the moment map which intersect the G orbit. Was G orbit intersect this level set, right? So I will give you a proof in a second. So I just sketch the proof of these theorems just to see how it works, and then I can generalize it for the non-reductive case. But the stable locus is the same point where both points was orbit actually intersect the regular part of the zero level set. So the regular part is naturally kind of corresponds to the stable set where the differential map is surjective to the dual of the Lie algebra. And so we have inclusions. So the zero level set sits in the semi-stable locus, and the regular part sits in the stable locus for this action. And these inclusions induce homomorphisms for the quotients. So this kind of the symplectic reduction is isomorphic to the GIT quotient, and this geometric quotient of the regular part by the compact subgroup is isomorphic to the quotient of the stable set by G. So So the sketch of, and the idea of the proof is the following. So we have two parts. So let's take A and B, and then the C part. For the A and B part, the key observation is that if you take the norm square of the moment map that serves as a moment map, serves as a Morse function on X. So it's kind of a Morse bot function. So we have not necessarily, we might have degenerate critical point set. So it's not necessarily just points, but we have high dimensional critical point sets. And so the open stratum of the corresponding Morse stratification, which then k-equivalently restricts to the zero level set, which is the minimal value. That's the minimal zero is the minimum of this. That coincides with the GIT semi-stable locus for the action of G on X. And so since, as you see before, so if you have the A direction of the moment map, the gradient of that can be identified I times the infinitesimal action of A for any A Lie algebra element. So the components of the gradient flow sit in G orbits. And hence for any semi-stable point, its orbit intersects the minimum critical set. And for X in other Morse strata, it flows to other critical sets. So that actually proves the first part. And then Francis shows that this Morse stratification coincides with the GIT stratification. So for the last part, to set up this isomorphisms, what we need is kind of a slice theorem, which is given by the gradient trick. So we really want to see that if you have the zero level set of the moment map and you have a point in that, and the GX of that, then the compact group preserves the level set, and we see that the complex part is it actually acts orthogonally, so it moves out the points. So the zero level set serves as really a slice for this action, the G action. And that's the gradient trick which we use. So X is a smooth manifold acted on by a Lie group H. And the trick, I put down this trick because this comes up. This is kind of the main and most sits in the heart of the proof for the non-reductive case as well. So this reductive slice theorem or gradient trick provides and gives you this slice property. So let F be any function X on X, smooth function. And let's take Y sitting in the zero level set of F. It's a union of finitely many compact connected components. Now, if you take any Lie algebra element, and if what we want to have is that F increases along the vector field generated by A. So if you take the infinitesimal action and that F increases along that vector field, then what is true is that if you take a point in Y and we kind of apply this flow, so you take the action, this A action on that, the action generated by A, then we never come back. That's the idea, right? So if you take for the zero level set, we can never come back because we know that infinitesimal, it always increases. So it moves out from this level set of the point. So that's kind of the geometry behind. So, and if you apply this principle or trick or this component of the moment map, so mu x, the A component of the moment map, which is denoted by Fx, then it turns out that this holds. So it's really F, this function, so this component increases along the infinitesimal action. And therefore, if you have a point in X in the zero level set of the moment map and G acts on that, then it will never return. So it will only stay there if the element, this G which acts on Y sits in the compact subgroup of maximum compact of G and K. So this means that we can identify. So we'll just take it short. So this means that this zero-level set of the moment map is really a slice for the action, and we can identify the quotient by the symplectic quotient. So if you quotient out by the k action on the zero-level set, it's the same as the GIT quotient. So that's the theorem. So what was in parentheses the thesis is that if you take it as a moment map, then it gives you the GIT stratification, and the stratification is equivalently perfect. So moreover, we can use this stratification to describe Betti numbers of the strata, and this combined with the curve and surjectivity gives us cohomology formally for the quotient. So that's the picture for reductive in the reductive case. And the question is how much this can go through for non-reductive situation. So first of all, we would like to come up with some non-reductive, so the analog of moment maps in this situation. And so in order to do that, because I'm running out of time, I just explained how to define this moment map in the Kähler situation and the algebraic setup. So if in the Kähler setup, we have a X sitting in a Y, which is a compact Kähler manifold, and X is a closed complex submanifold. And we suppose that we have an action H, which is a graded group on X, and we have this graded by this one parameter subgroup lambda. And because it's a complex reductive group, it's a complexification of K, and this G as X actually on the ambient space Y. So then, without loss of generative, we can pick R as being the complexification of Q, where Q is the intersection of the maximal compact subgroup with R, which is the same as the intersection with H, because there's no non-trivial compact subgroups in the unipotent group. So kind of we can assume that the maximal compacts are aligned. And so we define the moment map, kind of this is a rough and short definition, is so what we can do, we have this embedding of X into Y. Now Y has a G action, right? Sorry, H action. I'm sorry. So what we have is that G acts on Y. So G is this reductive group which contains H. So we have this reductive group G acting on Y. So we can take the normal moment map, the K moment map for this action on Y. So that's a map to the dual of the full dual of the real dual of the Lie algebra of K. Now that one sits in the complex dual of G. So we can identify the dual of K as sort of a real dual of G. So those elements in G star, which actually sit in R, and then that definitely sits in the complex dual of G, which is just the fuel, which is the complexification of this real dual. So this we can use. So we can compose the K moment map with this embedding into the complex dual, and because H is a complex reductive complex group, so it's a complex Lie algebra here. H sits in G, so there's a natural projection of G star to H star. So we can do that. So this is a composition now which maps from X to H star. This is what we really want to think of as a moment map for the action of H on X. And this is what we will call actually moment map from X to H, for X, for the H action. in the algebraic setup, we can put down this is in concrete formulae, like we have an analogous formula as in the reductive case. So we can be the same setup. If you have X is a projective variety sitting in Y, which is in this case Pn, then we have the natural G is GLN, and the maximum complex subgroup is a unitary group. So we have, and with the Fubini to the metric, we have we can write down this composition directly. And it turns out that the A component of that moment map is given by the same formula as before, but in this case, this is just a complex number. It's not real anymore, right? So for any Lie algebra element, this component is a complex number. And in fact, we can write down the real part and the complex part and to study this moment map then. So this is what we do. So, but this is the same definition as here, just but in this very concrete setup where we have the algebraic, when we have an algebraic action. So yeah, so the setup is that again we have a projective variety endowed with the linear action of U hat. Then we have a canonical U-hand moment map, in this case, as I just described. And what we proved is that is the following theorem. So this is an analogous theorem as for in the gradient in the reductive case. So we have the zero moment map for this U-hat moment map sits again in the semi-stable locus of U-hat over the U-hat action. And we assume in this theorem that semi-stability equal to stability, semi-stability equal to stability. So it's the same as the stable locus for U-hat. And then again, the embedding induces a homomorph, like it's actually a diffeomorphism of the quotient of this what we call non-reductive symplectic reduction. So in this case, again, we quotient out by the maximal compact subgroup of U-hat, which is in this case just an S1 because U-hat contains only one C star. So the maximal compact is just an X1. And that is isomorphic to the what we have seen the non-reductive GIT quotient. And so this is this is a non-trivial fact, but provides some sort of evidence that the construction which we have for this non-reductive GIT actions and the quotients is canonical. So it has a really a symplectic side and the same theorem holds. And actually, this is very useful for cohomological computations, as we will see. So the yeah, because I have only 12 minutes. So this the proof actually again, like for the non-reductive blow-up procedure, it's a little bit more supple and more sophisticated as for the reductive case. In this case, let me just say in short that the heart of the proof again is a non-reductive gradient trick, which is in this case not as obvious in the sense that we have to work with the two components of the I will not explain the details, but we have to work with the two components of this moment map. So there is the C star moment map and the component of the C star moment map in the direction A. And there is the full age moment map. We have to work with both and we have to combine the geometry of the two to come up with a similar slice theorem as for the reductive case. So as you see, we have two different functions, f and g in this case, with certain conditions along the initial conditions about the growth at the level sets, and that but kind of a very similar implication, and that gives us the slice part of the theorem. I will not go into details now. So the point is that since we have this description, so this isomorphism, that helps us a lot in cohomological computation. So and in particular, we can kind of integrate on non-reductive quotients using this description. This is what I will explain today and most probably also tomorrow in the first half of the talk tomorrow. So let's start. So what we now do is we would like to study the topology of this non-reductive quotient and Betti numbers and cohomology theory for the quotient. So we will use this picture in this study. So first of all, what we will see, this is kind of like a generalization, but on the other hand, much more simple picture as for the reductive case. So the GIT stratification in this case can be replaced by a very much simpler stratification, which consists of the stable locus and U times Z mean. That's the semi-stable locus. So X mean, which is just this Brioli-Scribble stratum, is the union of the stable locus and U times Z mean, as we know. And this is what is true, that this is again an equivalently perfect stratification. Which gives us expressions for Poincare series. So, like for the Morse stratification is equivalently perfect in the reductive case and in the Curwen's picture. This is again like a much simpler two-term stratification, which is again equivalently perfect. But so in this case, the quotient, the Poincare series for the quotient have a very simple expression. So it just means that we have, it can be expressed through so that's Z mean actually by the X mean C star is Z mean. So it can be expressed through the Poincare series of Z mean. So I'm sorry for this. This is a typo here. This X mean C star is Z mean. So once we know this, the Poincare series for Z mean, it's kind of easy to express the Poincare series, the Betti numbers for the full quotient. And again, we use that. We just proved that the equivalent Euler class of the norm bundle is not a zero divisor. So this is really a very simple situation in this case. So we just from this fact it follows this formula. Now. This is an example which I will not go through. Now, more than that, so this is Betti numbers from the stratification, but we can also describe integral formulae for these quotients. And that comes from this non-reductive symplectic reduction picture. So for that as an introduction, I will start with the reductive picture just to see how we generalize this for the non-reductive case. And so we start this reductive situation with an abelianization process, which is due to Sean-Martin, which really kind of a diagram which explains how we can relate the topology of X mod G and X mod T, where T is the maximum torus sitting in G. So we have the following diagram. This is from Sean-Martin. It's a paper from 2000. So we can take so we have a torus, right? Maximum compact torus, maximum torus sitting in G. This is the complex torus. So we can look at on one hand, we can look at the GIT quotient by this maximal torus, which is a torus is a reductive group, so just the same as the symplectic reduction at the zero level set of the torus, right? So this is for T is for the compact torus. So this is the T moment map here. On the other hand, we can take the full reductive group G and take the GIT quotient by G. That's the other end. And that's the symplectic reduction by the maximum compact K. Now, there is an intermediate space here. This is where you can take the same level set for the K action, but you only quotient out by T. So T sits in K. And then one can identify the vertical map, so the horizontal map as an embedding with normal bundle. It kind of is a bundle associated to the root spaces. So it's a negative root set for G. And that's kind of the interesting part in this picture. So this tells us that, and this vertical part can be identified. So the vertical bundle is just really correspond to the positive root spaces in G. And Sean-Martin's classical results tells us that the cohomology, so there are three parts here. The cohomology ring for the GIT quotient by G is isomorphic by, we take the, so the annihilator yeah, so this Euler class. So sorry, so E stands for the product of these of the root spaces, the product of the weight corresponding to the root spaces. I just didn't put it here. So that's an equivariant class. So that corresponds to the annihilator of E, and you can describe the quotient of X mod G as dividing out the invariant part of this by the annihilator of E. And another incarnation of this, if you rewrite this in isomorphism as the following, in terms of integration, if you take any form, so A is a cohomology represented by a form on the quotient, which actually can be lifted as a form on the quotient by T, then the integral of A over this GIT quotient by G is the same as, there's a normalizing factor here, but is the integral over the T quotient by the corresponding form times E. And in this case, E is just, again, is the product of the Fernstern class of these root spaces. So this C alpha, this is line bundles. So you can think of this E as kind of being the dual of, roughly speaking, the equivalent dual of the Lie algebra of T in G. And then we know that for torus actions, we have a residue formula. So the integrals over the GIT quotient by tori can be described as sort of residue formula. This is called the Jeffrey-Kirwan residue. So if you combine these two, we have a residue formula for quotients of integrals over quotients on X mod G. In the non-reductive case, we only use one part of this picture. Is the following. Again, we have two. Again, we have the same setup. So you have just a U hat. So U hat is a C star intersection of U by a C star. You can take the C star quotient, which is reductive. So it's going to be the symplectic quotient for the S1 moment map. Inside this, there is a X mod U hat, which has the same as we just saw there this description. So this is the symplectic quotient for the U hat moment map by S1. And then this is the part of the diagram which we actually use, which corresponds because in this case we would like to kind of the picture is simple. We would like to compare the C star quotient by the U hat quotient. And in this case, again, what happens is that here we have a normal bundle. Normal bundle can be identified by the roots, in other words, the weights of the adjoint action of C star on the Lie algebra of U, which are all positive, as you know. So we started with the graded action. So these actions are positive. So these are non-zero weights. Yeah. Yes, I didn't, yeah, we assume that. I'm sorry, I didn't, yeah. So this doesn't work for when we have strictly stable, semi-stable points. Yeah, okay. Yeah, sorry. Yeah, in the reductive case, we can have finite stabilizers, right? Even for so, especially if you work with, especially if you work with Q coefficients, then the finite stabilizer do not matter. So we have some, so we don't work with torsions, right? And so what the point is that maybe I should have mentioned this in the previous slide. So this symplectic reduction picture only works when semi-stable equals stability. So we have finite stabilizers. And that's why this picture only works in that situation. So we don't have a similar formula, integration formula in the situation where we have stabilizers. Yeah.
That's an extra point.
So that the T stabilizers are finite for the semi-stable locus for G. That's true. I mean, the G stabilizers are finite, right? And yeah, and then yeah, what you mean is that the T. Yeah, let's assume that. Yeah, I think that's the answer. The right is assume that. Yeah. Yes. Yeah, sure. What you mean is that the T semi-stable locus is bigger than the G semi-stable. Yeah, but let's assume that. Yeah, in this case, because that's otherwise the picture is not true right here. So I would like to use this picture, right? So I would like this equality to be true. Okay, so here's I just maybe just quickly go through the theorem. So what we prove this is again, I guess maybe just focus on the integral formula. So given a cohomology class A sitting in this, which represents, so there's a cohomology. So what you think of this, mainly we talk about bundles over this quotient, and they come from, so any Chern number of that bundle comes from an equivariant Chern class for an equivariant bundle over X. And we talk about this A as an equivariant form. But more generally, if you have any cohomology element in A, then we can, again, there's a lift of that to the C-star quotient, and the same equality holds. But in this case, we have to take the Euler class of this VU. So VU is just really the associated bundle of where it was, Chern roots are actually equal to the weights for the C-star action on U. So this is in practice, this is just the product of the weights for the action of this grading C-star on the Lie algebra of U. And hence, if it is a C-star action, this is the Jeffrey-Kerven local residue formula has a very simple form in this case. So I just formulated for this Chern case in this situation. So we can integrate any Chern form of a vector bundle V over the U hat quotient, and that is given by the residue formula. But in this case, we have only one residue variable because we have a C-star action. So this is just a C-star action, and it can be rewritten as an integral over Z mean of the corresponding form, when we have to divide by the normal class of Z mean sitting in X. So that's kind of, so the picture is that the message is that Sean Martin's picture goes through for the non-reductive case with a very natural substitute for the root spaces. In this case, this is just the root spaces are really replaced by the weights for the C-star action on the Lie algebra of U. And I stop here.
Okay, great, thanks. Any questions?
Yeah.
Yeah, so for the non-reductive case, this extra choice of internal grading, how much does this choice matter for everything?
The extra choice of?
Like this lambda going from C star to the...
Or for the non-reductive case. So for lambda in general, we'll determine Z mean, because Z mean is just really the minimal weight space for that one. So and it will not. So it affects Z mean, and therefore it affects the quotient, and also it determines what the blow-up centers are. But yeah, and so the question is how this will.
Let me rephrase.
Yeah.
For example, in reductive GIT, we have like this variation of GIT by changing the linearization, where we get birational. The different GIT quotients are birational.
Yeah.
Does the same happen with this other choice? So is there some kind of wall crossing?
Yeah, the same happens. So if you change, so there's kind of the variation of GIT here has two components. One is the linearization. The other one is the choice of your grading one parameter subgroup. And in some sense, in short, changing this, if you change the grading one parameter subgroup, then it will change the quotient, but it's kind of a very simple birational move described as the same way as in the reductive picture, but that really affects the quotient as well. So yeah, they have a wall crossing phenomenon here as well, but there's a two versions. So either both for the reason of having this grading and also for choosing the linearization.
But they're still birational.
Sorry, they're still birational, yeah. Yeah.
Thanks.
So I guess that in the theorem you told us about the symplectic reduction for non-reductive GIT, the hypothesis that the unipotent radical is linearly graded, I guess it's fundamental. But for the actual definition of your non-reductive moment map, that hypothesis is not needed, right? But
no.
So you can make sense of, so you cannot make sense of the identification, but itself the concept of moment map in non-reductive setting, you can do it in non-reductive.
For the moment map picture, we don't use, at least to define the moment map, you don't need the grading, right? To have the picture, you heavily use the fact that it has positive weights. So we have this U hat. So for the symplectic reduction picture, we heavily use that. For which, for example, in this gradient trick. So it's very important, but to define the moment map, actually you don't need.
Thanks.
Oh. So when you stated the symplectic reduction theorem, you stated it for like this U hat and S1. So could it have worked if you took H and Q instead of U hat and S1?
Yes.
Like for more general reference?
Yes. Okay. Yes.
And is the proof just doing it in stages?
Yes, that's the same statement if you replace U hat with H and S1 with the maximum compact in H. Okay. You have to, for the action, they have to be aligned as kind of explained. So we have this ambient space where the action extends to a bigger reductive group, for instance, and the maximum compact of that must be aligned with the maximum compact of your H. But beyond that, everything goes through.
Okay. Thank you.
Any more questions? Okay, if not, let's thank Gergely again.